Hello, Earth Science students, and welcome to a quasi short lecture slash overview of radiometric dating. Um, in this, you're going to be using a Google Doc that I'm going to be posting on Schoology to help you record some ideas as I cover them. You're going to answer a few beginning questions, and this will hopefully give us some good info to do a quick lab on Thursday and Friday related to how we use radioactive isotopes to measure the age of different things. Now, there's a couple things I want to talk about before we get to isotopes, and it has to do with the complications of dating materials, rocks or fossils, when it comes to their age. The first is that there's destructive forces, the things that shape rocks. So weather, erosion, climate, wind, ice, water, all of these forces constantly change the exterior of the surface. So, for example, Camel's Hump used to be 7,000 feet tall. It's now 4,000 feet tall because of ice sheets. And all of that 3,000 feet of rocks and historical evidence was destroyed. And there's also constructive forces. So, the Andes or the Himalayas are mountain ranges that are constantly growing due to plate tectonic shifts. And the hardest thing is that most evidence of living matter, things that are carbon-based, fossils, of plants and animals, often are degraded or decay in a few years, which makes it really hard for us to date things. So this is an image of a waterfall in Cornell or Ithaca, New York, and it was dated to about 380 million years ago, and it's limestone and shale, so it's some nice types of sedimentary rock, and these were formed in a basin from the eroding mountains known as the Acadian Range, which formed 380 million years ago. This was the same orogeny that helped create big parts of the Green Mountains. Now, the question is, how do we actually know the age of something? How can we figure out how old something is when we weren't around 380 million years ago to record it or write it down or take a TikTok of it? How do we know how old something is? And one of the pieces of evidence that we use is known as radiometric dating. Now, radiometric dating works only if a couple things are true. The first is that the daughter isotope is the source of a radioactive isotope, and we're going to be learning about what a daughter and radioactive isotope are, and also that isotopes are in a sealed rock. We're going to be explaining more of these things as we go throughout the lesson today, but I just want to introduce the idea of radiometric dating with this short video.
The carving of Mount Rushmore was completed in 1941, but the rocks it was carved into were completed quite a bit earlier than that, 1.7 billion years ago. How does a geologist know that? And how do they know that the Earth is 4.5 billion years old? The answer is a technique called radiometric dating, which lets us tell the age of certain types of rock. Radiometric dating relies on the fact that certain elements have what are called isotopes. These are versions of the atom with extra neutrons in them. Each radioactive isotope decays at a consistent rate. These measurements give us something called the half-life, or the amount of time it takes for one half of the isotope to decay. When an isotope's half-life is up, half your original element will be gone, transformed into a different isotope. Another half-life and you're down to a quarter of your original amount. A half-life after that and you're down to an eighth, and so on. The length of a half-life is different for every isotope. If you wait for enough half-life...
Sorry about that. Oh boy. I'll get back to this.
So to date something relatively recent, you want an isotope that decays quickly. To go older, you want an isotope that decays very slowly. The term carbon dating refers to dating using carbon-14, which we mentioned earlier. It has a half-life of 5,700 years, and most of it will be gone by about 50,000 years. To date things that are older than that, you want an isotope that decays very slowly. Uranium-238 has a half-life of 4.5 billion years. so it can be used to date things as old as the solar system itself. How do we use this to get the age of something? The unstable radioactive element that you use is called the parent, and the stable, happy isotope you end up with is called the daughter. Dating only works if the only source of the daughter isotope is the decay of the parent. You also need a rock that behaves a bit like a sealed time capsule, preventing daughter isotopes from leaving and keeping new parent isotopes from wandering in. That way, if you end up with half daughter and half parent isotopes, you know that one half-life has gone by, since the rock kept everything locked into the same place. Certain minerals form a tinker toy-like cage around any larger isotopes. This locks everything in place and makes for an excellent time capsule. Zircon crystals, for example, can trap atoms of radioactive uranium inside them, as well as its daughter isotope, lead. So, measure the proportion of uranium to lead in a zircon crystal, and you can figure out when it must have formed. Take this tiny zircon, for example, which would fit comfortably on the head of a pin. Believe it or not, this tiny zircon, which comes from Western Australia, is the oldest piece of Earth we've ever found. It's an absolutely mind-blowing 4.4 billion years old, and comes from when the Earth was only 150 million years after its formation. The zircon was dated using two different isotopes of uranium, uranium-235 and uranium-238. This provided a built-in cross-check, as you had two different clocks keeping time within the crystal. Whichever clock you look at, they give the same result. The uranium's been trapped in that zircon since it formed 4.4 billion years ago. Most dating techniques only work with certain types of rock. You can tell when lava erupted, for example, but can't figure out when sandstone formed. That's because the sandstone doesn't trap isotopes in the tinker toy-like cages that we mentioned earlier. Because there are other ways to tell how old things are in the world, we can compare those results with radiometric dating and show that they match. Trees, for example, put down a new ring each year they grow, and you can count backwards and figure out how old the tree is. You can also use carbon dating to figure out how old a particular ring on the tree is. Just like trees, ice in the Antarctic lays down a new layer each year, creating a similar ringed pattern. We can then compare that to the dates given by rocks trapped in the ice and show that they also match. If radiometric dating weren't reliable, we'd see differences between the results generated by it and those generated by these other methods. Fortunately, radiometric dating is reliable, which means if we go to Mount Rushmore, we know we can touch rocks that are 1.7 billion years old.
So this video I'm going to share with you, so if you need to go back and rewatch it again, you're more than willing or able to do that. And we're going to talk about these 3 slides where you're going to be able to take some notes on to further our understanding of what radiometric dating is. So the first, as alluded to in that video, are isotopes. Now, some elements, atoms, are formed with extra neutrons in the nucleus of an atom. I like to think of the nucleus of an atom as like a VIP club or a really cool place to hang out with, where you can't have too many people in it or suddenly it doesn't become cool anymore. So when we have isotopes with more neutrons in them, such as carbon-14, suddenly we start to strain the ability of that VIP club to stay intact. And we're really overwhelming the strong force, which is the force that helps these positively charged protons stay together. So when we have extra neutrons in the nucleus of an atom, that atom becomes an isotope. It's radioactive, and it's going to want to get rid of those extra peeps in the VIP club, and that tends to happen at specific time intervals. Now, the number of protons determines the element, not the neutrons. So for carbon-12, 13, and 14, we have 6 protons for each of these different isotopes. The key distinction is how many neutrons do we have, 6, 7, or 8? The general pattern is the more neutrons there are in an isotope relative to the stable atom, so 2 more, 1 more, the more likely it's going to be radioactive, and the shorter the lifespan will be. So carbon-14 is going to be more radioactive than carbon-13. So the second thing we have to talk about is radioactive decay. This is the process in which we expel, get rid of the extra peeps in the VIP club. So if isotopes are radioactive and they're not stable in their nuclear composition, they are going to kick out, bounce, so to speak, the people that are making the VIP club not so VIP anymore. So due to this instability, they usually send off some sort of charged particle in order to achieve a new stable VIP club. They're going to expel some of those extra neutrons and some protons just in order to get back to a small, more quaint, but also exclusive nucleus. Now, the frequency of this discharge is constant for each type of isotope. It might be 1 year, it might be a million years, it might be 500 million years. The discharge rate per atom is very consistent. So if we have a sample of a lot of uranium-238, which is a parent radioactive isotope, every 500,000 years or every million years, half of that uranium, the half-life is going to be discharged, resulting in new stable atoms. And that's going to be what we know as the daughter isotope. So this is where things become really interesting in terms of half-lives and radioactive decay. Each radioactive isotope has that half-life where a certain period of time results in 50% of that unstable isotope, the VIP club that became a little too popular with too many people, emitting and getting rid of those extra neutrons to become stable. Now what that means is if we look at the amount of radioactive material in an object, every half-life we're going to go from 100 to 1/2 of that initial amount. So we can go from 1 to 1.5 to 1/4 to 1/8 to 1/16 based on the amount of radioactive material in that object, but also what is the half-life. So by measuring this change in the nuclear isotopes over time, or by looking at the ratio between radioactive to stable isotopes, we can easily age objects. So if I find an object with carbon-14 and it's 25-75% stable to radioactive, that means that at least 2 half-lives have occurred because I only have 25% of the initial carbon-14 in there, while 75% might be the stable daughter isotope. This becomes increasingly difficult based on the half-life of an object because at a certain point there only might be 1/100th or 1/1000th of the radioactive material relative to the daughter isotope, so sampling and measuring becomes harder. So here is some quick questions that I want you to answer for class on for Friday. What is the reason why some isotopes are radioactive and what force is overwhelmed? For each isotope, what is true about the frequency of a radioactive discharge? And here's 2 simple math problems. Carbon-14, which is a radioactive isotope we use for carbon dating, has a half-life of 5,730 years. So it'll take 5,730 years to go from 100% to 50% and another 5,730 years to go from 50 to 25. If I have 100 grams of carbon-14, how much will I have in 22,920 years? A helpful hint might be to divide this number by this number and see how many half-lives occur. Carbon-14 also has a half-life of this. If I have a 100-gram tooth with 20 grams of carbon-14, how many years will pass until there's approximately 1 gram of carbon-14 left? We will go over these concepts more and go over these problems more in class. Please email me with any questions or concerns that you have, and office hours on Wednesday are always a great place to come with some extra questions or help. Have a great Monday, and I will see you tomorrow as we finish up our candy lab.